in France. She held postdoctoral positions under the guidance of A. Ziegler from University of Edinburgh, Austria, and G.I. Opat from University of Melbourne, Australia, where she continued her research into the area of atomic interferometry. In 1999, she joined the group of T.W. Hans in the Max Planck Institute of Quantum Optics in Germany. After this, she returned to Ireland in 2000 in order to take up the faculty post in Cork Institute of Technology. In 2006, she transferred her post to the University College Cork, and thereafter, since 2012, she has been in OIST Graduate University in Japan. There she leads the light matter interactions for quantum technologies. She is an active fellow member of both the Optical Society and the Institute of Physics. We all are honored, ma'am, to have you here for this talk. Thank you so much.
So thank you for the invitation. Can you see my screen?
Yes,
ma'am.
You can see the screen. Okay, so if there's a problem, let me know because I won't see if there's a problem, I think. So I'd like to thank you very much for giving me the chance to speak to your student chapter today. It's 5 o'clock in the evening here in Okinawa on a Friday evening, in obviously a very strange time for everyone around the world, but we make the best of it. I think one thing that I think is good from the pandemic is that people are more willing to have Zoom meetings, so it's easier to talk to groups of students around the world compared to getting on a plane, flying and spending a day with them. So I'm going to talk to you about some of the experiments that we do here in Japan on Okinawa. And here in the background, you can see the sort of environment that we have in Okinawa. It's very different to what many people think of Japan. You think of high buildings and neon signs and high technology, but Okinawa is actually quite a rural environment. It's got a very dense population, but much of it is rural, and the university is located in the less dense region of the island. So where are we relative to where you are? About 5,000 kilometers, so not too far. So normally India is one of the closer countries we feel for interactions. And we end up having actually quite a lot of our PhD students coming from India. I think it's because the climate is quite similar to areas like Bangalore, and that's quite pleasant, and also because Okinawa, the clean air, the safe environment, I think is very attractive to students from India. So here's our campus. So this is just the edge of what we call Lab 2, and this is where we have our laboratories. And down here in the background, you can see our engineering support section where they do the machine shop work for us. So OIST, if you're not familiar with it, I have to do this small advertising slide initially. So we started 10 years ago, so we're going to celebrate our 10th birthday in November. And it's an international PhD program. So what we mean by that is that there's no preference given to students from any nationality. So all nationalities are eligible, and all nationalities get equal funding. So there's no sort of bias in any way. The program is 5 years, so students can enter with a bachelor's or with a master's. And housing is on campus if students want. For the first year, we recommend strongly they live on campus, and then sometimes some students decide to move off campus, but most students live on campus because the accommodation is very comfortable. So we're currently closed for 2021 entry in September, so we're accepting for 2022 entry. But one other alternative is, so students can apply to the PhD program directly, or we also have what's called an internship program where students come for 6 months, work with a research team, and if they perform well, they can then be nominated into the PhD program. So I think the internship is also equally competitive probably to the PhD entry, but for students who are interested in entry before September 2022, it's an option, because through the internship program you can start maybe in January or May, so we have different times. So I said, nice environment, and outside today looks roughly like this at the moment, so it's always a nice view. This is the view from my office actually, so it's a nice view that I get from my office. Okay, so I'm here to talk to you about science, not tourism. So I'm going to talk to you about particular experiments that I do, but I've got 3 laboratories, and each laboratory looks at very different platforms as research systems. So in one laboratory I have we look at neutral atoms, so it's in a cold atom lab where we look at more or less atomic physics, nonlinear optics, electromagnetic transparency, Rydberg atoms, so highly excited atomic systems. So that's one laboratory. In another laboratory, we look at particle trapping, and I will talk a bit about particle trapping today, but not using standard particle trapping, which we consider to be optical tweezers, but more some of the methods that we have developed in our laboratory. And what we do very often is look at light in a confined geometry. So if you start seeing these images that I'm showing, the upper one here is an optical nanofiber, which is a fiber which acts just like a normal optical fiber, only it's down in the hundreds of nanometers diameter range. And here we have other confined geometries. So these are small spheres of glass. They can be hollow, they can be solid. These 2 happen to be hollow. And again, the light is confined to propagate within the wall of the glass. So it tends to be a very confined scenario as well. And you can see here in the background, how do we get light into these glass resonators? We use the same type of fiber as we do for interacting with our atomic systems. And these are very much, both of these topics are very much sort of physics or photonics background. But we also have an area in my group which we call the nanobiooptics group. And this is largely for interdisciplinary research. So we do some very fundamental research in this section on light behavior in the confined geometries, but we also do some very, very unusual work. So for example, we've had projects looking at mouse brain activity while they're freely moving. We've had projects looking at how coral bleaches according to different wavelengths of light that we put on it. And also our most recent interdisciplinary project has been looking at the distribution of plastics in the waters around Okinawa, where those plastics may primarily come from, whether they're a threat or not. And it turns out, fortunately for us, there aren't too many plastics in the water, so we don't really need to be concerned at the moment. So these are the 3 main topics within the group, and it's going to be sort of about the nanofibers, so this nanofiber as a coupler, and also these microbubble resonators that I'll talk about today. So first of all, I think you need to understand some more about these optical fibers, what makes them so special compared to a normal optical fiber. Then I'll talk to you about 2 different applications. These are quite visual applications. So even if you don't have a background in this area, hopefully you will get to appreciate some of the techniques that we can use and how these can be applied to different areas. So the introduction to the ultra-thin optical fibers. Most of you or all of you will know how normal optical fiber works. So it's ubiquitous. I'm not sure what the scenario is with India by now, but I guess a lot of areas are using fiber in order to have internet coming into businesses, universities, possibly even into some homes. Here in Japan, of course, almost everything is fibered by now, so fiber to the home is extremely common. And in optical fiber, there are 2 main parameters that we need to worry about, and these are the refractive index of the core material and the refractive index of the cladding material. So the light propagates through the core, and the way it propagates in a very simple ray picture diagram is through total internal reflection. So as the light is propagating, it hits the boundary between the core and the cladding, gets reflected back in, and then undergoes multiple reflections. But of course, that's a light ray diagram, and what we really need to use is a wave description of light behavior. So the refractive index difference between the core and the cladding will dictate this propagation behavior, if we try to think of some simple way. And another thing that will dictate it is the size of the fibers. So more or less, I can say the size of this core. If it's a very small core, I have what's called single mode fiber. So you can view that as I can't put too much data transfer down my fiber, but what I will transfer is a very clean signal. And at the cladding, then we're not too worried about. So we try to minimize the loss into the cladding and keep the light in the core. So I just spot a spelling error. This should be the pattern here, not patters. So here's a schematic of single mode fiber. It's just taking a cross section, essentially half a cross section through it. We're looking at the core, which has a certain refractive index, and the cladding surrounding it has another refractive index. They're both glass materials typically, just the core will have some maybe rare earth ions embedded in it to change that refractive index slightly. So you can see that the change is quite small. So from a typical cladding refractive index of silica, or SiO2, is about 1.444, and then of the core you get 1.4475. So it's a bit, we need the core to be bigger than the cladding. If I want to look in more a wave picture, so what does my optical profile look like as it's propagating through that fiber? So we can imagine this black boundary. This is just a MATLAB plot. The black boundary indicates the boundary between my core and my cladding. And for a single mode fiber, I mentioned that this is just a very clean optical mode that's going to propagate through the fiber. It's like a Gaussian pattern. So the maximum intensity of the light will be at the center of the mode, and then we'll have a decay as we go outside. So if I imagine this region outside my black grid there to be the cladding, I can see that it's going to be very little light in general in the cladding. So this is how it's designed to make sure this happens. This is called the weakly guiding regime in optics, where the refractive index differences is very small and the light gets confined to the core. So in the nanofiber or the ultra-thin fiber, what is different? Well, these are very thin glass fibers. So we reduced the size of the fiber from about 125 micron down to maybe 300, 400 nanometers in diameter. So what you're doing is here, you have your normal optical fiber, then you heat and stretch the fiber. So it's just like taking some toffee or chewing gum. So you're pulling it, and it's getting thinner and thinner in the middle region. Then at the edges, it's still the way you started. So you have normal fiber input, normal fiber output, and in this region here, you have the compression of the material, so very, very thin region. And if I think of my optical mode, so I couple some light into my fiber, it propagates in the fundamental mode. So I have a single mode fiber, looks like a Gaussian. In this region here called the transition region, that mode starts to spread out. And this is because we're now changing the ratio of the diameters of my cladding and my core. So I'm making my cladding, it looks smaller and smaller, and my core is getting smaller and smaller. This is the region of interest here, the waist region. In this region, I've reduced my cladding and my core by this roughly the same amount. So let's say a factor of 50 or 100. So my core now is effectively negligible. I can ignore it. And what my cladding does is my cladding acts now as the main guiding material for the fiber, but it needs its own cladding. So the environment around the fiber clads the cladding essentially. So what has happened to my refractive indices is crucial. Here, I now have the guiding material is the refractive index of my cladding, and the cladding material is the refractive index of the environment. So this will be air or water or vacuum, whatever you want to put it into. So let's see what happens to our fiber and the light. This was my scenario for the strongly guiding regime. I have a fiber of diameter 800 nanometers, so it's quite small, wavelength 633 nanometers, but it's still essentially a Gaussian beam with most of the energy confined within the fiber. I make my fiber smaller than the wavelength of the light. More of that energy starts escaping outside the fiber. So now we can imagine we have an interaction that's going to happen in this region here. And as I get smaller and smaller, you can start seeing even the maxima are now pushed outside the fiber material. So I no longer have a Gaussian type behavior. So here, instead of having intensity mainly confined within the fiber, in this case, it's mainly outside the fiber or near the surface of the fiber. And this gives me access to hugely intense light fields because the area over which the light is confined is tiny. So if I compare this to a free space beam, you're saying, okay, so what have I essentially done? I've taken a light beam and I've tightly focused it due to this changing fiber profile. And in the region where it's tightly focused, it'll propagate as a very tightly focused light beam. If I want to do this in free space and I want to focus a light beam down this small, first of all, I almost can't, okay? We typically say 1 micron is about the limit of what I can focus my beam to. Here, I'm several hundreds of nanometers. And the second crucial thing is if I'm focusing light, I hit this Rayleigh limit on how long, over what distance that light will be tightly focused. So you might call it the Rayleigh limit, the Rayleigh range. And this is really short. So if I focus light down to 1 micron, maybe I can work with that focus light over 10 micron or so. So certainly not over a long distance. However, for my ultra-thin fibers, where I've focused effectively the light down to several hundred nanometers, this can be several centimeters long. So I have a much longer interaction region. So instead of just being able to do an interaction with something, say imagine a molecule or an atom over microns or tens of microns, I now can do it over millimeters or tens of millimeters. So I expect to get much stronger signals. The other crucial thing here is focused light is non-paraxial. So the beams are no longer propagating along the axis direction. The same is true for the ultra-thin fiber. So these are non-paraxial propagation. So a lot of what you learn in optics as an undergraduate hits a limit and it's no longer valid. So some interesting optics effects become apparent when you work with non-paraxial regime. So here's how we make them. We have a hydrogen-oxygen flame here, and this is our fiber that we want to work on. So it's on several translation stages. We scan our hydrogen-oxygen flame. It's a very small flame, very hot flame. You can't see it. While we're scanning the flame, we're also pulling these translation stages. So this is like I was saying, pulling the chewing gum. And it's just making this region hotter and hotter and thinner. So you can start seeing this region glowing white, and that means we've reached the point where the glass starts to melt. So it's not melted, it's just starting to deform. And this is how we can maintain the shape. So it's not going to start dripping down like really melted. It's just soft enough that we can play with it. So when we have done this, we then monitor the quality of the fiber. And here's an example. So we put light through this very thin fiber. This one's probably reasonably big at about 1 micron. And when we see all these bright spots on our fiber, we know it's a horrible fiber and we have to throw it away. So I said that what we end up with in these systems is light that will interact with the environment. But we don't want that environment to be dust. And that's literally what you're seeing here. So every point of dust that lands on my fiber creates a scattering point for the light to interact, and it's a loss in my system. So when I have a really good fiber, I shouldn't be able to see anything. So if you look right at the left edge or the right edge of this, you don't really see any problems, and that's because it's cleaner section of fiber. So we need it to be extremely clean so that the light that I put in one side propagates out the other side with almost no loss. And any loss that we do have is due to the interaction I want to study, not just due to having a dirty laboratory. So these are pretty cool tools to work with. Everyone coming through the group essentially has to learn the first thing, how to make these very thin fibers. So let's put a context on the size. This is a normal optical fiber on the upper plot, where you have a single mode, so small core and large cladding. In these cases, the core of the light is about the same size as a red blood cell, so a few micron in diameter. This is a human hair. Human hair is about 50 micron in diameter, and here's a 2 micron taper fiber. So we're working with things that are much thinner than a typical human hair. The electric field, or the intensity of the light around the fiber, is very high. The reason being that we have an evanescent field. So this field is a decaying field from the surface of the fiber. We say its decay length is a couple of 100 nanometers. So we have all that energy confined into a cylinder around the fiber. It's still just a fiber. So if we take one of these fibers, we can tie knots in it, we can loop it around. We don't do this very often, but it's possible. You also just can connect it to other fiber. It's just a fiber, so really easy to connect to lasers, light sources, detectors, any of these sort of things. So this is a real advantage. You end up with a fibered system with very little loss. Here's an image of a more complete image of a fiber. So this is from the group of Dieter Mechte in Bonn. So here you have your single mode fiber, 125 micron. Here's your nice tapering region down to the waist, and then if you go down, 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 you eventually end up with your very thin fiber region much further down. And as I said, the very thin region is usually for maybe half a centimeter, a few millimeters. So what's the light doing in the fiber? So I've said to you before that in a normal optical fiber, light typically looks like a Gaussian mode. And we can describe this using a certain form of symbols to describe this, the LP01. So the LP means it's a linearly polarized mode. These are approximations. So this one here is equivalent to the Gaussian. So it's how we describe an optical mode within an optical fiber. So the LP description is the usual way where some approximations have been made. So a normal fiber, if I make it small enough, it'll propagate light in this pattern. If I take an image of the beam profile as it's hitting a screen, it will look like this, the LP01. Then if I have some higher modes, so I don't have a single mode fiber, but I have a few mode fiber, I might have pattern like this, the LP11, the LP21, LP02, LP12, and so on. And these numbers here, the 1, 1, will tell you how many nodes are in the fiber, and they'll also give you some information about the type of light that's propagating through the fiber. So the basic system we have mostly working with is this LP01, and we design our nanofibers so that it looks like that until we have the light escaping through the evanescent field. LP11 then is the next group. As I said, this is an approximation. So in reality, it's not the LP11. There are many modes present. And how would we excite this in our fiber? Well, instead of just coupling a laser beam into the fiber, we would couple a donut mode. So like an annulus, and light of an annulus shape coupled into the fiber will allow this mode to propagate. And so on, we can determine how to measure each of these. So which will propagate will depend on the size of my nanofiber at the end, the same as with single mode fiber versus multimode fiber in normal optical fibers. So if I make a small nanofiber, it'll be the LP01. If I make a bit bigger nanofiber, I might have also the LP11. Now, where do people use these nanofibers? I don't think this is an exhaustive description because it's already almost 10 years old. It's from 2013 by Li Tong. He's one of the people who really started strongly the research into these optical nanofibers. And we can see they're used in optomechanics, they're used in plasmonics, so you can put gold coatings on these and create plasmonic materials. They're used in quantum and atom optics, and I'm not going to talk about that today, but you can do atom trapping using these fibers. They're great as probes because they're so tiny, they don't disturb your atom cloud, so really useful in atom optics. You can use them to couple light from other quantum emitters very efficiently into fibers, so you can put a quantum dot at that very thin waist region, and then you get light coupled in. They also can, as I said, you can tie knots in them, so they can be operated as microcavities, which we have some images here. You can create miniature interferometers with them. But what I'm actually going to talk about primarily is as a coupler into a device. So a little bit different to here, it's going to be the optical coupler. So first of all, particle manipulation, then as an optical coupler. So let's start with the particle manipulation. So many of you will be familiar with the concept of an optical tweezers, where very tightly focused light beam captures particles in it. And in this picture here, we have a heart shape, and it looks like we have many, many beads within a heart shape. And what this represents is, in fact, a single beam that is focused very tightly, and then we move that beam very quickly in whichever pattern we want. So it's a colloidal solution, so there are lots of beads, about 3 micron in water, and then you're just moving your light beam to design out this pattern. So when you do your optical tweezers, you end up with things like this. You can nicely see the Brownian motion of the particles. Also, they're trapped, but each time the the trap is moving, so it's a time average trap. And once the trap is no longer on this spot, for example, the particle can try to escape, but we move so quickly that we get back there and trap it again. And there is a story behind this. One of my postdocs, researchers, was working very late at night, and I can't remember if it was his birthday or his wife's birthday, but all I know it was at 3 a.m. in the morning, and the wife she was at home and she wasn't happy. So he set up this heart-shaped optical tweezers to send to her to celebrate the birthday together, so that she would let him continue working a bit later that evening. So it's a nice little romantic story to go with our optical tweezers. And of course, the optical tweezers won a Nobel Prize in 2018 for Arthur Ashkin, and had been developed many, many decades ago, around in the 80s, early 80s. For us, we use optical tweezers, but we also combine them with our nanofibers. So here's one of our very thin fibers. It's in the same bath of particles as the optical tweezers. And what we do is just put light going from left to right through this fiber. And you can see that the momentum of the light starts pushing particles along the fiber. So we have an tweezing effect, or an optical force that pulls the particles towards the fiber. And then once the particles are near the fiber, the evanescent field around the fiber is strong enough to counteract any other forces that might be present and starts pushing the particles along the fiber. So you can start seeing scattering on those particles, and that's essentially light scattering. Similar to where I said if we have dust on the particle, we get this scattering effect. So the advantages of using the fiber compared to the optical tweezers, well, one thing is it's just another platform to look at, and now we have some type of linear motion or particle transport. People can study particle transport depending on the size of the particle. You can also do separation of the particles depending on the material. So if you have a few different particles mixed together, some of which might absorb the light, some of which don't have an interaction with that light, you can get different speeds and the particles start to group together. So it can be used for a few different things along that line. You can get also different directions of particle propulsion depending on whether it's an absorption or a scattering effect. Other features that we can get from this is that the light polarization is really crucial. So if I have linear polarization going through this fiber, or if I have circular polarization going through this fiber, I will see very, very different behavior on the particle motion. I'm going to show you some of this sort of behavior later. It's quite a complex topic. It's related to the spin angular momentum and the orbital angular momentum of the light. And it's a very long-term project that we've been working on probably for about 10 years already by now. So the first thing I'll talk about is something simpler. This is work we did in the lab, and then the theory was developed by Helmut Rich in Innsbruck. So this is optical binding. So we have these fibers. So this is just a micrograph. So this is 3 different images taken at 3 different times. We use optical tweezers to capture particles. So in this case, you can see that we have 4 particles captured by the optical tweezers, and then we move those particles next to the optical fiber. Second image, turn off the tweezers, just turn on the light of the fiber, and then the particles start to propagate along the fiber. And what we can see are that we get these nice chains of particles, and that they distribute themselves uniformly in a way that we can predict theoretically. So this is optical binding. It'll come into vision again in a minute. So the separation between each particle is larger closer to the optical source and smaller further away from the optical source. If I pulled one of those particles out of the chain, it would redistribute itself. So it would really feel the loss of that particle. And this is again all due to light scattering effects. So the further down particle, this one closest to the light source, experiences more light scattering than the particles furthest from the light source. So what we've seen is that we can get very stable traps. So here I'm just showing propagation because it's more visual, but we actually can put light from both directions, and then we can get the particles just trapped in space along the fiber. The other thing we can do is look at this single mode. If we have just the Gaussian beam coupled into the fiber versus if we couple donut beam into the fiber, how does the particle motion change? And we can see that it changes quite dramatically. For the higher order mode, or the donut beam coupled in, the particle moves about 8 times faster than for the fundamental mode. These are the same fiber. So this just tells us that there's a lot more energy in the higher order mode. So a lot more of the energy in the light is accessible to us by using the higher modes. So then we got onto the much more sort of fundamental behavior of what's happening to the light in this regime. And as I mentioned to you already, there are 2 features that we have for light and light's angular momentum. There's the orbital angular momentum, and these donut beams, things like this with unstructured light will often contain orbital angular momentum. And what orbital angular momentum has is that the wavefronts spiral along. So these are not planar wavefronts to the light. So this orbital behavior, if I put a particle here, the particle will follow the orbit of the light beam. And then we have spin, and spin is related to the polarization of the light. And if I shine spin or polarized light on the particle starts to spin around itself. So it's like a pirouette where you're rotating around yourself. So you get 2 different types of motion, the spin and the orbital. And it's quite hard to separate this. So to see the orbital is not always easy. So in our normal optics picture, we can really separate these 2 descriptions, okay? So they are independent and they are not interacting. And this is where we start using the pointing vector in order to describe the transfer of energy or through light flow. However, in this non-coaxial regime that we're talking about, where we're dealing with the optical fiber, it's no longer correct to separate the orbital and spin into 2 independent components. So now they are dependent upon each other. So if I have some orbital, I will likely have some spin. If I have some spin, I will probably have some orbital. So this is like a spin-orbit coupling, very different to the spin-orbit coupling that you might have heard of in atomic physics or quantum physics. This is spin-orbit coupling of light. It doesn't only happen in the confined regime. The other place where it can happen is if we have structured light, and that's things like these donut beams that I mentioned. So this is another one situation where we have non-coaxial. And what we're trying to look at the moment is this very small differences in light due to the regime that we're looking in. And in particular, what we want to see is a transverse spin component of light. And these spins the direction to what you would imagine if you just view it naively as the polarization of light. So in order to be able to study this, the first thing we want to understand really is the simpler case. What is the polarization of light meaning in one of these very tightly confined fields? So to do this, we need to be able to determine the polarization of light in the fiber, and we have developed a way of that so we can control the polarization quite nicely. And this opens up suddenly this whole regime of optics to us that couldn't be explored beforehand. So here's the setup. It's only a schematic. I'm not showing a picture because pictures, the experiments are really tiny, so photos don't really give them any justice. We have one of these optical fibers in a little bath of water. And here we have an objective lens, which is just for us to be able to image what's going on. In the bath of water, we have particles. So typically polystyrene, a couple of micron in diameter. And we're putting a beam in from both directions. Now, I said when the videos I showed, I only had a beam from one direction and you were able to see the propagation. Here, I put a beam from both directions. So we're going to trap the particle in this region here. So the momentum from both light beams will force the particle to stay in one position. However, what we can play with is the polarization. So we have a quarter wave plate here, and this will allow us to change the polarization of the light beams. So here's a video. You can see the beams aren't perfectly balanced. We have some movement along the fiber, but we can also see a rotation of the particle around the fiber due to the polarization of the light. Here, slightly better, higher power in our beams. SAM is the beam with polarization, so spin angular momentum. Better balance, so we're really seeing a faster rotation as well because of the higher power. And if we put a detector there, we just look at, on the detector, what is the scattered light, and we see a lot of scattering, little scattering, a lot of scattering, little scattering. The high peaks indicate the particle is in front of the fiber, we get more scattering, and the dark peaks, the fiber is behind the particle is behind the fiber, we get less scattering. So we have this optical frequency of the fiber, which is proportional to the polarization of the light beam. So if I change my polarization, I'd expect the rotation frequency to vary, and also I can influence that rotation frequency using the power in the light beam. Here's just some more pictures just showing you some nice optical binding. The particles start dancing together, even though they didn't see each other initially, they come close and they start interacting. So the other way we look at it, trying to understand what's going on in these particles, is using whispering gallery resonators. So these are very small, again, spheres of glass. They can be hollow or solid, in fact, typically about 50 to 100 micron in diameter. And we generate these whispering galleries within them by coupling light into them. These are really good cavities. So when you put a photon into them, the loss is very low. And that's how we determine cavity quality. So here are some examples of whispering galleries. You might recognize some of them, and that's where the term of whispering gallery for these little optical devices comes from. We focus on using microbubbles, which are hollow, so these have a very thin glass wall, and microspheres. And again, here you see how I get light into it. I just use the evanescent field from my optical fiber, and that couples into the sphere and then starts propagating around the equator. And these are used in many, many areas, but for one example here, they're used in single particle detection. So here's one of the resonators. We put light through the optical fiber. This light is at a certain frequency. When it's at a certain frequency, that number of wavelengths around the equator here is an integer number, which it has to be. Okay, we have to satisfy certain conditions for our light. If a little particle comes closer to my cavity, one of these purple particles in analyte sticks on the cavity due to this functionalization, what is effectively happening is two ways you can view it. My cavity is getting slightly larger, which means in order to be able to match my wavelengths for an integer number, I'm going to have to change the frequency of my light. Or you can view it that the refractive index is slightly changing due to the presence of the analyte. So when this purple here sticks on this functionalized component, I'm going to see a frequency shift on my light. So these are the sort of things that people look for. Here's without the analyte present, and here's the frequency shift due to the presence of the analyte. So here's how we make them. We shine a CO2 laser on a glass capillary, and we blow air through the capillary. So here's an example. This is a closed end microbubble that we're making. This is just a piece of optics. Don't worry about it. The resolution is a little bit bad always on Google. So you have a little bubble that creates here as you're blowing it up. And I mentioned that the quality of these resonators indicates us how long the photon will last. And these are very high quality. So a photon lasts extremely long time within these cavities. Here's again the pictures that can be used. We can break them to see how thick the wall is using a scanning electron microscope, and we see the wall is about less than 1 micron typically. And you can also make patterns of these, so you can have many cavities along the same capillary. And just have to move, sorry, I have to move something off the screen. In recent sensing work, you can use these for sensing. So you can imagine you've got some hollow cavity. Well, if you apply a pressure, the size of the cavity will change. So again, you'd expect to see a frequency shift on the light that is resonant with the cavity. So we've been able to do this with pressure, but that's not really our interest. That's just to verify the functionality of the devices. So the modes in these cavities are quite unusual. So if the cavity wall, so this is the wall of the bubble, this is inside the bubble where we put water, and then this is outside the bubble where there's air. And this is a third order mode, meaning I just have 3 maxima of light or light intensity within the wall. And then this is around the wall. So we've just made it planar for visualization, but you can imagine this is just a section of the wall which should be curved like this. If the wall is quite thick, you can see that there's not much energy or not much of the mode is leaking into the liquid. If we make the wall thin, we enter this very interesting regime where the light is guided by the glass wall, but most of the energy is in the liquid core. So this is what's called a quasi-droplet. So effectively the glass wall is containing the liquid, but playing very little role other than ensuring we're able to couple light into the liquid. And the refractive index that the system sees is essentially that of the liquid core. So this quasi-droplet regime proves to be very, very efficient for single particle detection, for biosampling, anything along this area. So one of the first experiments we did then was to try to see, can we spot the particles flowing through these? So we put fluorescing particles through. I have some parameters here. So these are quite large particles, 500 nanometers. They're excited at 532 nanometers and they emit at 630 nanometers. We couple light into the resonator via a fiber, and this is where we're going to look for a frequency shift. So if we wanted to determine how many particles are entering the evanescent field, effectively changing the size of our cavity, we would see frequency shifts on this light through the fiber. But all we're going to look at the moment is the particles being trapped in this device. So if I put light in here, it's going to act well like momentum transfer to any particles that interact with that light. So we look at some videos. So yeah, here. So hopefully these will play. So I'm going to turn them all on because I find again on Google Meets that it can be a little bit slow. So here we have particles on each video. The particles flow from top to bottom, and I wish they would play here, but okay, here we've got them playing, at least of one of them. So the particles are flowing from top to bottom, and in some of them we've got different powers of light interacting, so you can see very different behaviors. So on the left screen, we can see the particles coming in very slowly from top to bottom. They then start interacting with the evanescent light field, get caught in the evanescent light field, and then this bright field that we can see going around the equator is due to the scattering from the particles. And in the one here on the right-hand side, you can see what we call the caustics very nicely. So these are the modes in these cavities oscillate up and down along like the way I'm moving the mouse. And we can see that the particles have been caught at the extremities of the optical modes within the cavity, but also around the equator. The middle one, which I'm not managing to get to play, let's see, no, just maybe. This is actually the fastest rotation that has been recorded using any of these cavities for doing the momentum transfer to nanoparticles. Here, unfortunately, it looks very slow, but it's actually faster than the ones that are playing. But it's quite hard to see because of because the resolution and the bandwidth. So the next thing we did was, okay, instead of having the particles rotated, if we want to do any particle analysis or identification of particles, the particles really should be stationary. So instead of putting this evanescent field that couples into the whispering gallery through one direction, we put it through both directions. So similar to the fiber, here now we have particles going through our capillary. In this region, they're captured in the whispering gallery mode, but the whispering gallery mode now has two directions, one from each end of the fiber. So this light will propagate around in this direction, and this light will propagate around in the opposite direction. So if they're well balanced, the particles should end up being caught. And I know this in this video, we should see that there's a particle captured, and then here you can see it moving very, very slowly. Then we turn off one of those lights, and you can see that the particle is no longer captured in one position. It starts rotating again around the whispering gallery. So this is really useful, as said, for single particle detection. So what we went on to then was to look at chemical reactions using these. And this is work we do with a bunch of chemists in the USA, led by Randy Goldsmith. And what they're interested in doing is, I guess, particle spectroscopy on the single particle level. So what they started with was they took a series of nanorods made from gold. And these nanorods can be changed in shape by interacting them with ferric chloride. So ferric chloride, they have this as a solution, and this reaction is activated by light. So if they just have the gold nanorods, no light in ferric chloride, they're not going to see too much. If they turn on light, the activation here is much more dominant. And it's the type of activation or etching that they get is dictated by the wavelength of the light. So here's their schematic. Again, they have one of these bubble cavities. The pump here is going to do the photo activation. And here's their fiber, where they're just going to look at the frequency shifts that occur as the particle here is changing. So again, it's like you're changing the resonance of your cavity via the size, so therefore your wavelength or frequency of light that's coupling into the whispering gallery mode has to change. So the two things they want to do is get spatial and morphological information of a single nanoparticle during one of these photoactivated chemical reactions. And they also want to see, can they determine information about these nanorod orientation on the surface of the materials. The experiment itself is fairly complicated setup. So again, here's the bubble. They're flowing their solution with the chemicals, with the nanorods through it and with this ferrichloric acid. They have all pump wavelengths, 3 different pump wavelengths for this photoactivated etching. Those wavelengths just go through a series of optics where they can control the polarization and the focus, and that's used for imaging the particles inside the chamber and also used, as I said, for this photoactivation. Then they have another wavelength here, that's a tunable one, where they're looking for the frequency shifts in the experiment. So these are the very first images that they got, okay? So they have their bubbles, they're flowing nanoparticles through here. You can start seeing these bright regions where they have the nanoparticles. One image here is out of focus, the other image is in focus, so they're able to play with the depth of imaging, and then they're able to play with the color. So here they're using a red beam in order to do their imaging, but they can change that beam depending on what way they want to etch the gold nanorods. They can change the polarization of the light that they're using to pump. So again, the pump is this one, external, where they're doing the photo etching. And what they have are these nanorods. So as I said, the nanorods are going to change in ratio or change into dimensions as they start to do this chemical reaction. And there are 2 possible plasmonic bands that can be generated. There's a transverse plasmonic band, which gets activated if they're using light in a green wavelength range. And there's a longitudinal plasmonic band, which is along the long axis of the nanorod. And this gets activated if they're using light in the red region. So for example, in the image here where they're using red light, you would expect that it's more likely if the polarization of the light is along the long axis, this should be the reaction that they're getting. And the nanorod will get shorter. Whereas here, if they're using green light and the polarization is along the transverse direction, so the short axes, they expect to make the rod thinner. Okay, so this is how the plasmon bands interact. So one will make it shorter, one will make it thinner, and we can control this through the wavelength. So here's a plot of what I've actually just been explaining, the normalized absorbance, and as a function of wavelength. They have 3 pump wavelengths. So they have this green one, the red one, and sort of this dark purple one. And depending on which wavelength they choose, they can choose a different plasmonic band. Okay. Is there a problem? Is everything okay?
This is okay, madam.
It's okay. All right. So here's the first image. So they have a very bright image, and they're using one of their polarizations. So if it's a bright image and the polarization is defined along the long axis, we know that it should be in this band, so the red band. If we had a minimum absorbance, it would have to be the opposite direction. So when they shine the red light, they get a very bright image. They know that their polarization is aligned along the nanorod. And then by changing the polarization direction for these 3 pump wavelengths, they just look at the resonance shift. The opposite case, okay, if they have the polarization along the short direction, they will expect maximum signal for the green and minimum for the red. So again, maximum absorbance, so minimum transmission. So these again are the plots. So all they do then is change the linear polarization of their pump, and they look at their images, these photothermal images, and they end up with a whole series of them. Okay, so for each of these photothermal images, they can determine the polarization of the light. And based on the image, they can then determine the orientation of the nanorod relative to the polarization of the light. They have three different colors, remember, and they do a full rotation of the polarization by 180 degrees. So it's, as I said, it's a little bit complicated, the setup. So what's actually happening? They have start off with a nanorod, they put it into this ferric chloric acid, they drive it using the linear polarization band, so that's the red wavelength pumping. Linear polarization band means I need my polarization along the long axis, so it's going to make my nanorod shorter. If my nanorod gets shorter, I would expect to have a different plasmonic resonance. So if I start off here and go here, I'm going to shift the behavior of the system. So over time, they look at what's actually happening. So they monitor the polarization angle, or they change the polarization angle, and they look at their frequency shift through the tapered fiber coupling into the microbubble. This frequency shift changes, so this is their frequency shift along Y. This changes depending on the size of my nanorod, because it's changing the effective size of my cavity. And over time, they just allow this interaction to process. So each of these is just over time, they monitor what's happening. So there's a lot of data in that plot, so then they pull out the important parts. If I look for the maximum signal for each of these time plots and plot it, they get a curve like this. So they see that the maximum signal is reducing over time. We can pretty easily see this. These bars here, these vertical bars, are just where the signal gets so low, they need to increase the intensity of the light in order to be able to continue the etching, the photoactivated etching. The other plot they look at is what polarization do I get my maximum signal? So we can see that as the polarization is changing, the position of my maximum signal is slightly changing, and they see this plot. So for my maximum angle, so my angle at which I get the maximum signal changes very quickly at the end. So initially there's very little change over my maximum angle, and that's for these red plots, but then it starts shifting quite dramatically over here. So after some time, there's quite a dramatic change in the shape of my nanorod. Now, what this is indicating, this was done for the LPB, so the red light. They also did it for the green, so the 532, so to do the transverse, and they didn't see much difference. Whereas every other measurement on this sort of chemical etching showed that these two wavelengths should behave dramatically different. I should get really fast etching if I'm using green light compared to red light. But on the single particle level, we don't see that change. So what's happening in the etching process, these are the nanorods, and during the fabrication of these nanorods, there is a surfactant used, which is called CTAB. And CTAB, when you clean your nanorods, after you've made them, you've synthesized the particles, you try to remove everything, there will always be some CTAB present. I flowed the nanorods through the Fe3 plus solution, the ferric chloric solution. Some of the iron ions bind on the nanorod, and then depending on the color of light I shine on the nanorod, I expect to get a fast interaction to change the shape, or I expect to get a slow interaction to change the shape. So that's what happens within the bulk. And what we have seen within the single particle, fast versus slow, there isn't really a difference, very, very minor difference. So what we're trying to now understand is why on the single particle does the etching not really get strongly influenced by the wavelength of the light? Because everything tells us that it should. So fortunately, they're chemists and they can understand a lot of what's happening in these interactions compared to us. We can make the devices and advise them on the optics, but then they can look at the chemistry. So the other thing that they looked at was, the final thing that they looked at was this effect. They're shining this probe on the nanorod, and the probe has a polarization. But imagine if the nanorod is not really tightly bound to the inside surface of the bubble. So we flow these nanorods through the bubble, they stay stationary, some of them as though they're sticking on the surface. but maybe they're not sticking on the surface. And if I change the polarization, maybe I'm changing the orientation of my nanorod. And this is what we believe is actually happening. So here I consider the microbubble wall. I imagine that I have the nanorod essentially stuck on the bubble wall. It's interacting with my light field, and I'm pumping it in order to get this etching process going. But it turns out that there's a very thin liquid layer between the nanorod and the microbubble, and this is a microfluidics effect. Therefore, when I shine light on the nanorod, which has a polarization, I'm providing an additional torque to the nanorod, and its orientation is changing. So even though I think that I have got the orientation of my polarization along the long axis, what's happening is it's rotating the nanorod, so my polarization is no longer exactly where I thought it would be. So what we thought we had this alignment nicely, you end up with this change in angle, and therefore you're no longer at the optimum plasmonic resonance. So you can look at all of this. We've done it from many, many different angles, many different orientations of the nanorod, and we have seen a uniform behavior that our signal changes as we vary the light polarization, regardless of the orientation of the nanorod. So there really is this very single particle effect due to the light's interaction. Also, if we look at the signal that we get, again, this is just looking at the light from the system, a photothermal map. Over time, as we're increasing the pump intensity, we start seeing we're pumping more and more light into the system. Yes, we're getting more and more light out of the system, and then we hit some saturation type point of view, and we believe this is where we end up with the scenario where the light re-kicks the particle off the wall, and then the orientation can start happening. So then this is the point where we start getting the torque on the nanorods from the light. So the next step is to really try to understand this process, because it's really down at the single molecule level at this point, and also to try to do some more functionalization. So these gold nanorods are relatively big. What we'd like to work with is a single molecule detection. Okay, so at that point, I'm going to finish up. Just to summarize, I explained to you some of the work we do with ultra-thin optical fibers for particle manipulation. We have other scenarios where we put slots in these very narrow regions, and we can trap particles within these slots here. I talked to you about some whispering gallery resonators, how we can use them for bulk samples, for sensing, for single particle trapping, but we also can try to use them for understanding actually chemical processes on the single particle level. And then some other work in a similar style, which I didn't talk to you about here, is plasmonic trapping. So we have some plasmonic structures, and what we're doing is single protein trappings. They're about 5 nanometers in size, so very small particle trapping. And we're trying to understand some mechanisms behind proteins folding and unfolding as they're trapped in these structures. Here's my group. This is the members currently, and as you can see, we're funded primarily through the university, but also we have funding through several Japanese public and private foundations. A few different nationalities. I think it's 14 nationalities in the group at the moment. And then these are our social media platforms. So I'd like to thank you for your attention. Thank you.
Thank you very much, Professor. Madam, it's exciting that we are having a very good session. So here some of our colleagues are there, some senior professors. So now I request all of the audience, if you have any questions, you can directly interact with Professor.
Yeah, so either ask me a question directly or through the chat, whichever is easier. Okay, so there's one question through the chat. My question is that while coupling evanescent light to whispering gallery resonator, does the fiber on which the resonator is placed also interfere in the detected signal? No, fortunately not. So we have, if we imagine, I'm not sure, I'd have to move my hand slowly so I don't interfere with my signal. If we have light coupling into the fiber, into the resonator, we tend to couple the light where any other fiber, so the resonators are made from fiber as well, or in our case here, we talked about capillary. So you're coupling light in a dimension that is different to the stems. Okay, so if I wanted to couple light in the same direction as the stem, yes, then the stem would interfere and I simply would have a very lossy system. But by making sure that you couple into the opposite dimension, so the opposite plane, you don't have a problem. So you just get very, very high coupling. So the very low loss system. Not sure if that answers your question. That was from Jaceline Cower. If there's any more questions, okay. So hope if I didn't explain the answer to you well, just send me an email and I'll try to explain it to you a bit better. Okay.
Professor, I have a doubt.
Yep.
That nanofiber what you make, so that nanofiber guide the light because it is it's become very tiny. So it is follow the total internal reflection Snell's law, or how they guide the light?
No, you have to use wave. You have to use wave equation description.
Wave equations.
So yeah, so this argument, you know, using the ray description where we're getting some total internal reflection simply doesn't work. We're at a scale where it has to be wave description. Okay, so you have to really start from first principles, solving Maxwell's equations, and then putting in some boundary conditions related to the material surfaces, and then you get the full solution. So the full solution of the mode propagation in the fibers is quite complicated. The easy description, you know, to explain things is, yeah, you're having this wave total internal reflection, but that's purely just a simple description. The reality that has to be the wave.
And this nanofiber can be made with chemical etching.
So we make them always using the heat source. So people can make them with chemical etching, but the problem is with the chemical etching, first of all, you can't control it so well as with the heat source. And the other thing is, chemical etching tends to give you a fiber tip rather than a solid fiber, rather than a full fiber. So if you want to do something with a fiber tip, I would say chemical etching may be better even, because you really can control, you're dipping into typically hydrofluoric acid. But if you want to have really it as a light guide, the chemical etching is not good, because it's just going to etch away the cladding, but the core will still be fully there. Whereas the heat and pull reduces the core and the cladding by a similar amount.
Okay.
So you've really changed, you know, you're really maintaining the fiber guiding properties. Whereas with the etching, you're losing the fiber guiding properties.
And these nanofibers are very much tiny. And how we can give mechanical support on these to handle for experiments and all these things?
Yeah. So it's actually very fortunate the way that glass behaves. So you'd imagine that if I have something made from glass that's only 500 nanometers, it's going to be extremely fragile. But in fact, if we think of glass normally, we're thinking of glass as a large item. So, you know, we're drinking water in a glass. And the cracks that can happen in glass at that size cannot happen when you go down to a couple of 100 nanometers. So the material itself becomes much stronger material than what we traditionally think of as glass. Now, of course, if I do this and try to snap it, it'll break. But it can take quite a lot of handling. And the way we mount them is quite simple. We just take a piece of aluminium metal, a mount like this, literally big, and we glue the fiber onto the mount using UV glue, which does index matching, so we have no loss. So remember, I have my nanofiber region is maybe a centimeter, but I have normal fiber everywhere else. So I glue the normal fiber so that my nanofiber region is free hanging.
Okay.
So it's quite fortunate that they're not as fragile as what you think. And I think people have done comparison with carbon nanotubes, and I think it's similar. Its tensile strength can be similar to that. So it's really, its behavior is different. Glass behavior is different at this scale.
Okay. Questions in chat box.
Yeah, there are questions here. Yeah. Since a tunable laser is expensive, can we use an LED source using a micro-ring filter to filter out the desired wavelength? So, sometimes we use broadband light sources, but I think for anything with the if you want sensitivity, you need to really have a tunable laser for this. So, I mean, we have some bad lasers that we just use to monitor the transmission. But if we really want to see the frequency shift, this frequency shift is tiny. So you would never be able to filter, you'd have a lot of problems filtering it out. So I can see you using micro ring filter, maybe some type of Bragg rating, but it's going to be challenging possibly, yeah. Then there's another question. Does the size of the particle matter to observe this phenomenon? What could be its orientation about the fiber? So we typically work with the spherical particles somewhere between 200 nanometers and maybe 2 micron. The reason we work with this size is that if we're trying to do particle trapping, we need to overcome gravity. Okay, and if the particle gets too heavy, it just sinks. So we have our little particle sample, a water sample where the particles are in there. If the particles are really big, they sink to the bottom, and then we have to try to get them up to interact with our light field. So, you know, it's sort of like a jiggling game. Juggling is trying to get the particles up. So if they're smaller, they're lighter, and they're more likely to just float in the fluid. And that means they're at the same level as the fiber or the cavity. So that's one reason why we stick with the certain size. And the other reason is that a lot of our experiments with the fiber, so not the cavity, but the trapping experiments with the fiber, we start with an optical tweezers. So we capture our particle using optical tweezers, place it next to the fiber, and then look at the interaction. Why do we do that? It's so that we can control the number of particles. If I just put the fiber into the particle bath, I will get particles, many particles trying to interact with the light. So if I have a very dilute number of particles in my liquid and just use optical tweezers, then I don't have so much problem. I really can control what particles are interacting. Optical tweezers needs very high intensity. And as I go a smaller and smaller particle, I need higher intensity. And at some point, you just evaporate the particle. So that's the other restriction. If we're using optical tweezers, we have to think of the material we're using, which is typically polystyrene, and being able to capture it in the optical tweezers, first of all. Now, we have some projects where we do gold or half gold particles, much harder to capture in the optical tweezers, but they love moving next to the fiber. So while the optical tweezers tends to be the limitation in the particle more than the fiber part. Hopefully that answered. And then it's the orientation about the fiber. So we always use spherical particles in my group. So the chemists, as you said, what I was talking about at the end, they were using the nanorods, and this orientation is really crucial. But we always use spherical particles. There have been times when we've used particles with chirality. So this would be more due to the molecular structure of the particle, so that it'll interact with the light a little bit differently. And that's just when we want to enhance some of the rotations that we see. So if the particle is chirality and we shine polarized light, depending on the polarization of the light, we should see faster or slower rotation. But they're still spherical particles, but just not totally isotropic, I guess. Would we see the same phenomenon with metal, non-metal, oxide, and other nanoparticles? Well, depends which phenomenon you're talking about. So I talked about the optical tweezers. It's very hard to do with metal. You can do it, but you need much more intensities because refractive index plays a role always in this. Other nanoparticles, yeah. We've worked with polymers. I said we've worked with liquid crystals. So yeah, if you can get the right balance between the intensity that you need without destroying the particle, you can see similar behaviors. People have done things for using, I'm trying to think, NV Center Diamond. They have a group here in Japan has recently moved that along these fibers. So you can, as long as you can get the right wavelengths, the right intensities, it should be fine. The research scholar working in speckle pattern analysis and fiber spectrogram sensors. Is there any research going on where particle trapping studies is being carried out along with the speckle pattern studies. Oh, I will never say there isn't to any question. I will never say no to any question, because I don't know everything that's happening in the world. So I would guess there probably are particle trapping experiments where people also look at the speckle patterns, but is there some fundamental reason why they can't because of the sizes? I'm not sure. So speckle patterns and things like this are really outside my domain. You need to talk to Kishan Dolakia from St. Andrews, because he does a lot, I think, with speckle patterns and particle trapping. But whether what extent he combines them, I'm not sure. Yeah. Okay, thank you. Okay, that's fine. I hope I've addressed all the ones in the chat. I said maybe not always giving a perfect answer, because I'm not omni-knowledgeable. We all have our limits, but hopefully I've answered some of them in some way. But I said, if I haven't, just email me, and then I can answer. So I'm just sending my email address on the chat to those people in case they're not happy with my answers. And they will have my email so that they can contact me.
Okay.
Now I've turned off dictation somehow.
Yeah, thank you very much. If any questions, so it is very excellent sessions, and we on behalf of the student chapter SPIE and from NIT Warangal, National Institute of Technology Warangal, we are thanking you once again for joining the sessions, for answering all the queries, and it's a very exciting and memorable session. Hopefully sometime we will get you here in offline mode. You will come here in our campus. So thank you once again, Madam Professor. I hope all questions, there are no more queries. So we'll conclude the session here.